Zhen-Su She from Beijing. He's on Zoom. We don't see you pinned just yet. Peter, are you there? Can you fix the pinning, please? Well, why don't you make a start, Zhen-Su, and we should be able to see you very soon, but I don't want to take up your time. So
can you hear me?
We can hear you clearly. Please go ahead. Oh, we see you now.
Okay.
Good.
Okay.
No,
Okay.
no. Okay. Oh, I know. It's because I'm talking. All right. I'm going to stop and over to you.
All right. Hello, everybody. Thanks, Bubbly, for inviting me here for this talk. My title is Multi-Layer Structure of Turbulent Boundary Layer and its application to engineering turbulence model construction. Here's my co-author, Wei Tao B, my colleague here. Okay, my goal here is to define mathematically the relevant statistical structures in the TBL, take into account the thin TBL, to engineering predictions of drag and heat transfer. And here's the two works and published in 2017 and 2018, which is the theory for this. So what is the multi-layer structure? They are simply the viscous sublayer, buffer layer, log layer, and the bulk region, which are familiar structure normal to the wall, but also include the laminar, transition, and the fully developed regions in the streamwise direction. So that there are two directions. We're talking about a two-dimensional developing TBL. So how to define that mathematically? We use this so-called stress length, which is essentially the mixing length. But also we have the length defined by three component fluctuation intensity components. Each define one length. We call that energy length. So all together, they are so-called similarity parameters, similarity variables for us. And we have a generalized Lie group invariance assumption, which yields the following formula. Here you see the multiplication of four terms. Each represents one particular layer, sublayer, buffer layer, log region, and the bulk region. The bulk region with a separate variable r is the distance to the center of the bulk region. Now, our assertion is that once they are quantified, just like these parameters are known, then all mean fields of TBL are fully prescribed. Okay. Well, most interestingly, that not only the mixing length, which is the shear stress length, but also the energy length, they all satisfy the same formula with the same sublayer thickness as you see here, and the buffer layer thickness, and also for the channel, there is a core, R core, and so there are four layer structure. Here you see on the right is the channel flow DNS data. Show the four separate the scaling, and this transition function, which goes from one scaling region to another scaling region, are coming from a generalized Lie group invariance assumption. Okay, the mixing length or the stress length and the vertical length, vertical energy length have a very good structure, but the streamwise length and the span-wise length, energy length, have a slight anomalous components effects due to, I call the meso layer, and earlier Ivan Marusik talking about large scale structure. They are essentially the same thing. So there are large scale structure which create a meso layer, and also for the span-wise component, there is a near wall strips. These two kind of structures generate a slight anomalous effects on this formula, but they are small. So we're looking for, let me give you some evidence of the validations. And these are the Stanford data, experimental data for the TBL for 4 different Reynolds number. And on the right is the vertical energy prediction. So here, there are not many parameters. The kappa equal to 0.45, it determines this L-ling, the coefficient in front. And the Y sub and Y buffer are essentially 9.7 and 41. They will become constants, and then the 9.7 will become universal constant for all wall flow, but Y buffer will have a slight variation, as we'll see later. So there's no fitting parameters here, and for different Reynolds number, and they're just the predictions. Now, let's talk about the complex wall flows. These are the canonical situation. For the complex wall flows will involve transitions. So there's streamwise variations. So therefore, we have to resolve the whole Rand's equation. This is the energy equation, this is the mass equation, and the momentum equation, and the energy equation. And all we need to define is this mu t, the eddy viscosity. And as viscosity now is defined by this the length, the stress length square, and stress length is, take the formula as you see earlier. This is the this is the normal structure, normal 4-layer structure. And here the coefficient L0 and the Y buffer will have a streamwise variation and describe the transition from the laminar. Here you see the, again, 3-layer structure. The first layer is the laminar part, and the second layer will be the transition part, and the third layer will be coming to the fully developed range. And in this, including the spanwise evolution, we now have 4 parameters. And the most important parameter, of course, is the transition center. Earlier, people used the transition location. And the transition center, we'll see, was the essential parameter we're going to define in describing various engineering flows. And there's another parameter, beta, which describes the transition strength, which describe for the incoming turbulence fluctuation, too strong turbulence fluctuation, there will be an overshoot. And that is described by with beta. So this is essentially a quantification of the transition region. And of course, the 2 other parameters will describe the fully developed region. So here is our transition model. And to just make a comparison to the Mantel's 4-equation model, they have a momentum equation and energy equation, and then the gamma factor, the so-called intermittency factor equation, and also the Reynolds number equation. And look at the complexity. And clearly, we are simplifying the system now. Now, let me describe you 5 different engineering flows that by increasing complexity. First, let's talk about a low-speed flat plate. The low-speed flat plate, as I said earlier, that we have to define the transition Reynolds number. Here is the formula as a function of the incoming turbulence intensity. So here we identify a critical intensity, incoming intensity with 0.65%. There's a percent. So in other words, that for incoming turbulence intensity much smaller than this, and this is the constant transition Reynolds number. And for increasing one, for much larger, which is called forced turbulence, a forced transition, and then there will be a scaling of minus 1.5. It's not so complicated. And let's look at the result. There's no other feeding parameters. All this 0.65 is a transition one, and also this transition Reynolds number at a very low incoming intensity. Here are result. Let me see, there's no feeding parameters. And there is SNK experiments, and then T3 series experiments, flat plate experiments, and also our colleague KTH DNS data. And looking for the first time that we can fit the data almost exactly. And our KTH simulation runs for a different incoming length scale, 3 different incoming length scale, and also 3 different incoming, this is a 3 different length scale. Let's look at next. Let's try to see how this compare with other prediction models. Essentially, the prediction models are the mentor model, most famous and most widely used models. And there are a few other teams to improve the mentors model. Here for the T3, T3A and T3B. As you see, T3A and T3A mentors model predicted pretty well, but T3B is not. This is T3B. And other models are, mostly are calibrated for T3A, and they are not doing a good job for T3B at all. Okay, so this is our, this is the formula I mentioned earlier, that now we're still, this is how the direct measurement of the transition location as a function of this this correlation. Now let's look at the other subsonic airfoil flow, and here is so-called RAE 2822. And there are different cases. This case 2, case. This is a plot of so-called polar curve, with the horizontally is the lift coefficient, and the vertical is the drag coefficient. So the experimental data are the black square, and the red square is our prediction. And on contrast, that the so-called SA model and SST model, which is the 2 most industrially used ones, so have deviations, have significant deviations. Now, if you look at the left here, that we have for the first time achieved an agreement with a drag coefficient of order of 2 counts. And the notion of 2 counts, one count is 10 minus 4. This is the absolute measure of the drag. The 2 count is the order of the experimental error. So we have reached this experimental error limit. Now another very famous, this is just to show the so-called pressure coefficient, the contour, and you see that the red is our model, which capture exactly the shock, while the SA model has a slight deviations of the shock. Now here, look at another very famous airfoil flow, which is called NACA 0012. NACA 012 is a symmetric airfoil, and we have run 40 different cases with different Reynolds number, different attack angle, and here look at different attack angle. Again, that to compare with SA model and SST model, you see that they all have a systematic deviation as a function of the attack angle, the error. But the new one, the new model doesn't have this systematic error, and all below 22% for the lift coefficient, and below 6 counts for the drag coefficient. And people wonder why 6 counts? Well, because this is a symmetric airfoil. For symmetric airfoil, that drag coefficient measurement has bigger errors, and their error limit is 6 counts. This is according to the literature. Oh, let's go from the subsonic now to hypersonic flow. Hypersonic turbulent boundary layer on the flat plate. This is the experiments by me and a company in 2002, Mach number 6. And you see the 4 cases here is 4 cases. The first 3 cases are the increasing Reynolds number. So for 1, 2, 3, increasing Reynolds number, you see the transition actually moving, turn up earlier. Okay, earlier and earlier. And here, the center of the transition follow another formula I'll come to later for hypersonic flow. And the last one is the high entropy flow, which is high energy flow, and which the transition actually is compared to the first one. Their Reynolds number is comparable. Okay, so all four cases are very well captured. They are heat transfer coefficient. This is heat transfer coefficient. Now let's look at the hypersonic turbulent boundary layer on cone, which is more challenging model. This is a very intensively studied by people around, and especially by the industrial people. It is tremendously difficult. It's described by them, but tremendously difficult because there are Mach number effect, Reynolds number effect, and temperature, the surface temperature effect, and the incoming noise level, and the noise radius, and the roughness effect, and angle effect, and half angle. So here is our new formula for the transition center Reynolds number, as a function of the Mach number and the surface temperature, and as function of the half angle, and also the nose radius Reynolds number, and also as the incoming pressure, incoming turbulence intensity. This last one is the same as for the earlier our formula for the flat plate. Oh, this is a hypersonic cone. Okay. Now with this, we have identified a few very interesting transition Reynolds numbers, and also the critical number for this the half angle. All right. So with this formula, that here, first thing that we did is there are a bunch of experimental data on the literature, and if you plot them, plot the transition Reynolds number in the horizontally, and also the vertically is the transition Reynolds number, and the horizontally is the incoming onset Reynolds number. This is a vertical is a transition onset Reynolds number. As a function of the surface Reynolds number, then you see that there's no consensus, no formula can represent it. But as we take out the effects using this formula, you see that all things collapse now to the single curve. Therefore, the transition center Reynolds number is predictable. And with this, let me show you that the new prediction. This is for the angle cone zero angle attack, and this angle attack of 2, 4, and 6. And we have we obtain the arrow bar much smaller than the improved mental model. Of course, the original mental model does not work for the cone at all at hypersonic speed. But the improved one take a lot of energies, and people has communicated to us, but still with the error bar much larger, at the order of several dozens, and ours generally is below 10. Here, just show you a few slides. This is for the NASA Langley Mach number 6 wind tunnel data. And this is a Mach 10 for the top, and the Mach 6 below, and for different Reynolds number. This is all from our European data of von Karman Institute for Fluid Dynamics. And this is just to highlight this Mach number effects, 5, 6, 7, and also Reynolds number effects, 0.72, 7.2 million, and this is 10 million, and this is 24.5 million. And they all well captured. And here, lastly, let me show you the hypersonic cone with incidence with, now this is a angle of attack of 2. And this is the angle of attack of 4. And this is the angle of attack of 6. All right, so finally, this is, there's a comparison of this called C gamma RE theta, which is the improved mental model. And this for angle of attack of 10, it captures roughly the transition location. But the angle of 4, 2, 4, 6, they are way off.
Zhen-Su, this is your 5-minute warning.
How? Okay. Finally, this is another case of Mach number 7 and angle of type 6. And you have seen the mental model doesn't capture at all this observed transition, and ours get pretty right. Finally, there is a hypersonic boundary layer on lifting body called a hypersonic transition research vehicle. And this is by CRDC. CRDC is the Center for Aerospace Research Development of China. And this is the model. And this is for the zero attack angle. Here is a zero attack angle, Mach number 6, and a Reynolds number 10 million. And this is on the wing, on the leaf side. This is on the back, and this is on the belly. This is a Mach number, a higher Reynolds number, 22.22 million, Mach number 6. Okay, so here is what I must mostly try to show with this very simple transition model. Now can simulate a wide variety of flow, and very from my last slides, I'd like to tell you that the theory also can be used to derive an analytic formula for the Monet-Alpert similarity function for open atmospheric surface layer. And I think the talk follow me that is going to talk about this. And we have this function for the first time where we are able to derive a non-adjustable parameter formula with no pressure effects. And we are able to represent the pressure fluctuation effects by the two parameter A and B. And the parameter, particularly parameter A, is the one which explain the shift of the carbon constant from 0.45 to 0.36. And we have an interpretation now. Okay, the conclusion. Okay, I think I want to make 2 points. First, the multi-layer structure is the most relevant statistical structure of TVL because they are stable and its accurate quantification is possible. Secondly, they are directly linked to engineering properties of TVL. So the engineers must know the multi-layer structure accurately in order to make a very accurate predictions. And why the present description is so accurate? Why so accurate? I think what behind our formula is a self-organization principle for complex engineering TVL flows, including transition. And you know, transition is a non-equilibrium flow, a property, but already from our sublayer to buffer layer, from buffer layer to log layer, this kind of non-equilibrium transition already take place. So why we can use the same principle to describe the transition from laminar to transition to fully developed regime as the same as from a sublayer to buffer layer to log layer. Finally, that the analysis I developed here is a symmetry breaking analysis. Our original title was via a symmetry approach, but the symmetry approach now I realize that what we are talking is more about symmetry breaking rather than the symmetry itself. So how did it break? The break is from a sublayer to buffer layer. That's a symmetry breaking. So these transitions are universal, and understanding this allow us to describe the more complex effects of the complex engineering flow with some additional feature with some layer parameter variation. So our take-home message is that the complex TVL flow is essentially a small deformation of the canonical TVL flow with that's a layer parameter variation. Here is my talk. Thank you for your listening. Lovely, this to you.
Okay, questions or comments for Zhen-Su? Well, I have a question going right back to the beginning. Could you walk us through again at the very beginning
Sure.
where the symmetry analysis comes in, and where, just for my edification, how you find the constants, and do they stay constant all the way through? I mean, I think the question is the underlying analysis. Yeah. Okay.
These are.
I mean, even on the earlier on the early slides. Yeah. Or okay. So
there's just the same as, right? Okay, this is the parameters here.
Yeah. Okay.
So the C12 will define the common constant if we know the Y sub or Y buffer.
Okay, but
And
but my question is, how do you find Y sub and Y buffer? So you calibrate that to a channel flow, and that applies across all these other flows.
Yes.
Okay.
Y sub is calibrated to the channel flow and also later to the pipe flow, and they're all the same. And the Y buffer, interestingly, Y buffer could have variations in all complex engineering flow, but in the canonical flow is 41. So we all know that the Y sub is somewhere between 5 and 20, right? We know this. Everyone knows this, but what is exactly this? So if we have a formula here, we would be able to use the data to define it. Yeah.
So do you do that for each flow then in the complicated case?
No. Now, for now,
so
probably next time you can use 9.7. Tell me if anything goes wrong. I'm claiming that 9.7 is universal for all wall flows.
Okay. And then the
and then Y buffer is around 41. Could vary by 5-10%, but it's
and the exponents there on each of those terms.
Exponent is fixed. Is by our analysis. Is fixed. It's 2, 3 here. 3.5 here. Is 1 here. Is 2 here. Is 1 here. There's nothing.
But those are you're saying those are analytical.
Yes. This is a paper. You can look through the paper.
Okay. And these expressions are holding into the high-speed regime, or those are different?
Yes. For the high-speed regime, here is look at this high-speed regime. That this two parameters, L0 and Y buffer, will have a streamwise variation, but the variation, the law is the same. Look at the same formula. So we're essentially identify a universal law which makes the transitions. Here is a transition from sublayer to buffer layer. Here is a transition from the laminar to transition to fully developed region.
Okay, here's a question from Rich.
Hi, I wondered if you could indicate what would happen to your theory in 2D. So if I was looking at 2D channel flow. Thanks.
2D.
Yeah, 2D channel flow.
2D channel flow. 2D channel flow that some parameter will vary, but the structure will be the same. Some parameter will vary.
So do you predict a log layer in 2D channel flow?
I would think so. The log layer in the paper, we have identified the log layer with isotropic dilation invariance. If I impose the isotropic dilation invariance, then it must come in with the log law. So I would say that for the 2D, it should have a log law too. I may be wrong.
Okay.
Log law is very robust.
Okay, we have a question from Martin, and that will be the last one.
Please. I can hear.
Hi, this is Martin. I'm asking about the you using the length scale, right, which is an eddy viscosity type of model.
Yes.
So,
yes.
well, I mean, this is probably reasonable. Okay, if you have shear flows or wall-mounted shear flows. However,
yes.
if you go to a very different type of flows, such as rotating flows or whatever, that concept does not work at all.
Yeah.
Can you comment on that?
Yeah, I think you're right. If there is strong rotation, then they will come with some other effects will come in. However, my intuition is that even for the rotational flow, there will be some variant of this type, and with perhaps another not shear. This is a shear induced length, right? This is a DYY for the denominator. So even with rotation, that there will be another length coming in, will have a composite length. Now this question is relevant because now we talk about, for example, the separation. The separation is coming with a pressure gradient. So pressure gradient will introduce some interesting new lengths here. However, the phenomenology developed here will still be useful. Yeah.
To wrap up the discussion now, but thank you very much for calling in your evening over there. So
thank you, and hope the whole success of the workshop. Thank you.
Thank you. Okay, so if you could stop sharing, please, Zhen-Su, and then we have Xiaojing Zhang